Alright guys, so this is our Thermochem crash course. I'm sorry that these videos are horrible. I promise I will make them better as we're preparing for the real exam. Activation energy is found from my reactants to the peak, so this is for the forward reaction. This is my activation energy for my reactants going to my products. You also have a reverse activation energy. So my reverse activation energy is from my products to my peak. So this is activation energy in the reverse direction. You can also see that on this exothermic graph. So my forward activation energy is from my reactants to my peak. My reverse activation energy is from my products to my peak. Moving forward to enthalpy versus heat. So we already defined what enthalpy is. It's an energy transfer. It's known as delta H, and my units are kilojoules per mole. Heat, however, is signified by Q. The difference between heat and enthalpy is that Q is measured in just kilojoules or joules. Your enthalpy, delta H, is measured in kilojoules per mole. So the moles is the difference between here. How we convert from one to another is delta H is equal to Q over moles. So if I have heat, which is Q, and I want to find delta H, I have to divide by moles there to get that. If I have delta H and I want to find Q, then I have to take my delta H value and multiply by the moles here to get my Q value. How we find Q is this equation here. Q equals MC delta T, or you probably hear me refer to it as MCAT. This is a list of all of the units and what they are. So C is specific heat. Remember that the specific heat of water is usually around 4.18, and that's what we use most of the time. M is for mass of the whole system. Delta T is your temperature change, which is final minus initial, and Q, of course, is the amount of heat transferred. Remember that positive Q means that heat is absorbed, and negative Q means that heat is released, just like delta H. Now for our enthalpy calculations. So we have three that we use most widely. Big Mama equation is also known as Hess's law. And delta H of the reaction is equal to delta H formation. This is very important right there. You have to use delta H sub F values. And what they'll do is they'll give you a big chart that gives you all of those values to be able to put together. Delta H of formation, what that means is basically how much energy is required to make a compound. So we're only looking at compounds here, how much energy to make a compound. So if I have single elements, like oxygen as a single element, iron as a single element, chlorine as a single element, aluminum as a single element, it doesn't take energy to make these because they're elements, they're not compounds. So all of those values right there are zero when you plug it into the Big Mama equation. Also, what you need to know is the delta H of formation is for only 1 mole of that compound. So if I have a balanced reaction and I have 2 iron 3 oxides, then I have to take the value for the delta H of formation and multiply it times 2 to be able to account for 2 moles of the iron 3 oxide. Remember that delta H is products minus reactants. Products minus reactants. Then you have system of equations. So system of equations is where you basically have one reaction and it'll have a delta H value. There's another reaction, another delta H value, and basically you have a goal equation that you have to create. So you're manipulating these two reactions to make your goal equation. remember that whatever you do to the reaction, you have to do to delta H as well. So if I take this reaction and I double it, then I have to double my delta H as well. If I have this second reaction and I have to flip it to where my reactants are now my products and my products are now my reactants, what you have to do to delta H is also flip the sign of my delta H. So when I flip delta H, I flip its sign. Once I have all of these reactions lined up to where I want them to be, and I'm creating my goal equation by adding these reactions, you also add your delta H values to find your final delta H. So that's how you work the system of equations approach. The last approach to find enthalpy is bond energy, and hopefully you guys will understand this a little bit better now that we've gone through bonding unit and we can draw these Lewis structures and everything. So how we work bonding energy, there's a little diagram right here that shows that equation. Delta H of the reaction, all right, so don't forget that bond energies is equal to delta H. A lot of people forget that. It's equal to the bond energies that are broken minus the bond energies that are formed. When bond energies are broken in our reactant side, and bond energies are formed in our product side. So if you pay close attention, you see that the Big Mama equation and this bond energy equation are actually reversed. So how I think of bond energy, the B, E for bond energy stands for backwards equation. This Big Mama equation, Hess's law, that is on your equation sheet for the AP exam, but the bond energy equation is not. So if you just remember that the bond energy equation is backwards from this Big Mama equation, you'll be able to remember that, and that it's also equal to delta H of the reaction. What you have to be able to do with these bond energies is sketch out the bonds. So if I have 2H2, I've got to be able to witness that HH is a single bond, but since there's two there, I have two HH bonds. And so that's why right here, we're multiplying that bond energy of an HH bond by 2. For O2, it's just an O double bond, and I just have one of them, so it's 1 times 494 for the bond energy there. And then H2O, this is our structure for H2O here. What we have is 1, 2 OH bonds, but since there's a 2 right here, I have to double that quantity. So there's 1, 2, 3, 4 OH bonds, and that's why we multiply that bond energy by 4. After you do that, you plug them in. Remember, it's reactants bond energy minus products bond energy, and that is equal to your delta H of the reaction. Moving on to entropy. So entropy is basically defined as disorder. Think of this as a molecular level. Are these molecules, are these atoms moving around in a chaotic fashion where they're very disordered, or are they moving in a nice, neat, ordered pattern? So we look at maybe if I have a solid in a reaction going to a gas. Solids are very ordered. Gases are very chaotic. They're moving all over the place. So this would be an increase in disorder, and we give increase in disorder a positive delta S. If I had, for instance, a liquid moving to a solid, liquids are more disordered. They're moving around less closely than a solid is. Then what we're doing there is we're decreasing the disorder in the reaction. Anytime we decrease the disorder in the reaction, we get a negative delta S. You can also look at whether or not an ion is breaking up. So let's say if I have a solid that's dissolving into its positive and negative ions, so that's its positive ion, that's its negative ion. What we're doing is we're having one substance create two different substances that are moving around. So this would be a positive delta S. If I have things that are all in the gas state, I look at how many moles of gas that I have there. So let's say to balance this reaction, I have a 2 here and a 1 here and a 3 here. On my reactant side, I have 3, 4, 5 moles of gas. On this side, I only have 1 mole of gas. So I have 5 moles of gas that are moving about versus 1 mole of gas that's moving about. 5 moles of gas are way more disordered. So if I go 5 to 1, I have a decrease in entropy, so it's a negative delta S. How we calculate delta S is the sum of my delta S of my products minus the sum of the delta S of my reactants. This is Hess's law again, or the Big Mama equation. And what I also have to do is multiply by how many moles I have in that balanced reaction. So if I had a reaction that had 2 of something plus 3 of something else, and it goes to Z, then I have to multiply the delta S value for X by 2 and the delta S value for Y by 3. So make sure you include those moles in your balanced reaction. One other thing that I want you to take note about is the units for delta S. The units for delta S are joules per mole Kelvin. Don't forget that, because we're going to have to convert that at some point. Now looking at free energy. Free energy is defined as the energy available to do work. So energy available to do work. How we find Gibbs free energy, there's lots of different equations. We learned 2 in electrochem, but this is the one we most widely use in thermochemistry. Delta G equals delta H minus T delta S. Delta G is measured in kilojoules per mole. Delta H is also measured in kilojoules per mole. T, of course, is measured in Kelvin. But look here. Your delta S is measured in joules per mole Kelvin. So don't ever forget that you have to always convert this delta S value before you plug it in, so our units will be able to agree with one another. Okay, so always convert your delta S to kilojoules. If I have a negative delta G, then that means that it is thermodynamically favorable. And if I have a positive delta G, that means that the reaction is thermodynamically unfavorable. Thermodynamically favorable reactions favor my products. Thermodynamically unfavorable reactions favor my reactants. Now, last but not least, are our sign conventions. This is very important. They like to ask all kinds of multiple choice questions about this. So, if I have, this is all referring to that granddaddy equation, which is delta G equals delta H minus T delta S. If I have a negative delta H and a positive delta S, then my delta G is going to be negative no matter what, at all temps. Doesn't matter what the temperature is, delta G will always be negative. It will always be thermodynamically favorable. If my delta H is positive and my delta S is negative, then my delta G will always be positive. It doesn't matter what the temperature is at all temps. Now, when delta H and delta S get the same sign is where we have to look at temperature. So, if both delta H and delta S are negative, the only time when delta G is negative is at low temps. So that's the only time when delta G is negative. If your delta H and your delta S are positive, the only time when delta G will be negative, is at high temps. So at high temps only, your delta G will be negative. So don't forget these. Also looking at delta G, if delta G is 0, then that means that K is equal to 1 and your E cell is 0. Remember, this is at equilibrium when this is the case. If delta G is negative, then K is greater than 1 and E cell is positive. And if delta G is positive, K is less than 1 and E cell is negative. So these sign conventions, they show up a lot in the multiple choice. The next thing we have to know is the Maxwell-Boltzmann distribution. So what we have here is you always have number of molecules on your y-axis, and kinetic energy or even speed can be on your y-axis. They can ask two different questions here. Which one has a higher temperature or relating temperature, or they can relate molar mass. Okay, if they relate temperature, then you basically have the same substance, so the same molar mass. And you look at the curve and which peak is dropped down furthest to the right. So this peak right here, the red line, drops down right there. This blue peak drops down right there. Okay, whichever peak is furthest to the right will have a higher kinetic energy. Now, how this relates to temperature is actually the measurement of the average kinetic energy. So if I have a higher kinetic energy, I have a higher temperature. So if we look right here on the x-axis where this peak dropped versus the x-axis where that peak dropped, we have a higher energy, kinetic energy, or even a higher speed. Those go hand in hand because kinetic energy is 1/2 times mass times speed squared, or velocity actually. So as the speed increases, the kinetic energy increases as well. So these all go hand in hand. This particular peak, the red line, has a higher kinetic energy, so that means that it has a higher temperature as well. Now let's look at molar mass. The molar mass is if they have the same kinetic energy or same temp. They have the same temperature, same kinetic energy. Most of the time what will happen is you'll have speed on this x-axis. When we look at speed, this one, the red line, has a greater speed than the blue line. So you ask yourself, do lighter things move faster or do heavier things move faster? So speed, the faster things have a lower molar mass. So they're inversely related. If I have a higher speed, which is this red line, then that means it's going to be the lightest molar mass out of the two. So it's going to be a lighter molar mass than the blue line. The last thing we have to talk about with thermo is our phase changes. Remember, phase changes are at equilibrium. So that means that we have a delta G that is equal to 0 here. You have to be able to tell if a phase change is a positive delta H, a negative delta H, or even a positive or negative delta S. So if we have a solid that is going to a liquid, remember that solids are the lowest energy state and gases are the highest energy state. If I go from a low energy state to a higher energy state, then that means I have to put in energy to get there. So that would be endothermic. So endo is a lower to a higher energy state. Exothermic would be a higher to a lower energy state. So let's look at the delta H's for all of these phase changes. A solid going to a liquid is melting or fusion. Since I'm going to a higher energy state, then that would be endothermic, so I get a positive delta H. Liquid going to a gas is going to a higher energy state, so we get a positive delta H. And a solid going to a gas, which is sublimation, that is also going to a higher energy state, so I would get a positive delta H for that. Anytime I'm going to a lower energy state, it's exothermic. It has to release energy to get to that lower state. So a gas to a liquid would be negative delta H. A liquid to a solid would be negative delta H. And a gas to a solid, which is known as deposition, is also a negative delta H. Now let's look at delta S. Delta S, whenever I have more disorder, it's a positive delta S, and less disorder is a negative delta S. So, gases have the most disorder, and solids have the least disorder. So, if I go from a solid to a liquid in this direction, then I am getting more disorder, so I have a positive delta S. If I'm going from a gas to a solid, I have less disorder, so it's a negative delta S. So they like to ask these questions a lot in multiple choice as well.